Hello everybody. In this video we'll look at section 1.3. We'll start the limits of inverse trigonometric function. The following theorem will help us evaluate limits that involve the inverse trigonometric functions. So first part, the functions arcsine, arccosine, and arctangent are continuous. And you could see it from the graph. We didn't lift our pen when we drew it, but they're continuous, which tells us a lot about the limits as well. And the arctangent function has two horizontal asymptotes. It has y equals plus pi on 2 and y equals minus pi on 2 as the limit as x goes to plus infinity. Let me just graph it here. Remember the arctan looked like this. This was minus pi on 2. This was pi on 2. And so if I go to infinity, I'll get a limit of pi on 2. If I go to minus infinity, that's this way, I'm approaching a height of minus pi on 2. All right, so I want to use these two limits and also the fact that the functions are continuous to evaluate other limits involving arcsine and arctan. All right, let's look at this one first. Whenever I evaluate a limit, the first thing I'll do is I'll plug in the value. It might not algebraically make sense, but it's going to give me a good idea. Because it's not always legal to do it, I'm going to put these brackets around it that tell you and tell me that I'm cheating. So I'll call these my cheating brackets. I know some teachers like to put quotation marks, that's fine as well, but I want you to show me that you know that this is not a real computation, that you could put it in a calculator, that it's a limit that we're writing as a computation. All right, and then I'm going to look at the inner part, e to the minus infinity. If you remember what the graph of e look like, it looks like this. So if I'm going, let me draw it for real so it stays, because I do think it should be in the notes here. I'm going to minus infinity, so I'm going this way. I'm approaching 0. And so really, this is going to be arcsine of 0. Now, this is no longer a limit because arcsine of 0 makes sense, and we know that arcsine of 0 is 0. Either using the calculator, or if we've computed it a few times, or just reminding yourself of that, sorry, I don't have it close, that table with the sign inside. All right, so one question you may ask is, I don't think I've used theorem 1.3.1, so why did we need it? Well, you know the interior goes to 0. And so one thing I'm using that I haven't mentioned is that I have, so the limit as x goes to minus infinity of arcsine of e to the x, that's equal, because the interior part is going to 0, that's equal to the limit as, let's call it w goes to 0 of arcsine of w. And what we did here was just put in the w inside and said that was arcsine of 0. This step here, this step of putting the limit, the value of the limit inside the w, that uses continuity. All right, so if you want me to talk about this a bit more, just ask me in class. That's Cal 1 material. You needed a bit this term, but I'm not going to quiz you directly on that, but you do need to know when you're allowed to do it and when you're not. All right, let's try again. Here is a new limit. I want to look at arctan of x squared plus 5x. So let's look at what we end up with. I have arctan. If I plug in infinity here, I'll get infinity squared, which is still infinity. 5 times infinity is still infinity. So really, the interior goes to infinity. And so I want to know, where does arctan go when the interior goes to infinity? Well, that is this part of the theorem. Arctan goes to pi on 2. All right, again here, what I want to do is I want to plug in the infinity in. If I do, The top's going to go to plus infinity, the bottom to minus infinity, and now I have infinity over infinity. I don't know what that is. In fact, we'll spend next week, chapter 2 is going to be in these indeterminate forms and how to solve them using derivatives. So this is one of the indeterminate forms, and so that means I cannot tell you what it is by just looking at infinity over infinity. I have to actually go back to the function 2x plus 5 over minus 2x plus 6. I have to go back to this and use algebra on this to simplify it to get the limit. So this is one of the indeterminate forms that we'll see in chapter 2. All right, so in chapter 2, we'll learn a trick to evaluate this, but in fact, this is one of the limits that you learned how to evaluate in Cal 1. So let's look at it. I want to look at the limit as x goes to positive infinity of 2x plus 5 over minus 2x plus 6. Limit as x goes to positive infinity, 2 plus 5 on x. I'm going to factor x. So my trick is usually that you factor the biggest power of the denominator. So in this case, I'm going to factor x out of the denominator and out of the numerator. Let me write it here. Factor the biggest power of the denominator. All right, and then these powers are going to cancel, so I'm going to cancel this x with that one. And then once I've gotten rid of the x is what gave me infinity. I'm going to get the limit as x goes to positive infinity of 2 plus 5 over x minus 2 plus 6 over x. When I plug it in, I get 2 plus 5 over infinity, that's 0, and then minus 2 plus 6 over infinity, that's 0 as well, so I get 2 over minus 2, which is minus 1. All right, not done. That's just the interior. So this interior goes to minus 1. Since arctan is continuous, that means the whole limit as x goes to positive infinity of arctan of 2x plus 5 minus 2x plus 6, that will be arctan of minus 1. Sorry, I'm a bit low on space. And that's minus pi on 4. I got a bit too excited with indeterminate forms and took too much space. All right, so I'm getting minus pi on 4.